is where we left off in the last video, and we were looking at the relationship with rates. So it's important to note not only at what point the rate is measured, whether it's instantaneous, initial, or an average rate, but you also want to make sure you pay attention to what the rate is measured with respect to. Because you see that NO2 decreases at roughly the same rate that NO increases, but oxygen's only half of both of those. So it's related to the stoichiometry, and since a reactant is a loss, we're going to put 1/2. The stoichiometry was NO2 going to 2NO plus O2, and that would be the change in the concentration. The brackets, remember I mentioned this earlier, mean molarity. If it's partial pressure, you have to put a P, not brackets. Okay, so it's 1/, the coefficient, and that's going to equal plus, because it's a product, we're gaining product, 1/2 times the change in NO per time, and those are both equal to plus 1/1. Obviously, I don't have to put that mathematically, but I just wanted you to see that consistency, that it's 1/, the coefficient, oxygen delta T. Now, a couple of comments here. One is that these deltas are really calculus. We would really use the letter D, concentration, dt. But we don't deal with calculus at this level. We're going to simplify things quite a bit. But those of you who are in calculus, I like to bring that up so you see that connection. Taking d something dt is simply taking the slope. Now, the other thing we can do is to simplify that is to write it instead of the deltas and all of that. We could say 1/2 the rate with respect to NO2 is equal to positive 1/2 the rate with respect to NO, and that's equal to positive the rate with respect to O2. Now, if we knew one of these, then we could always calculate the other. If we wanted to compare two experiments that measured the rates of slightly different, we could compare them using their stoichiometric coefficients. Now, this shows the generalized equation for that, so that hopefully it's a little clearer for you to see that there's the coefficient there, and it's 1/, that coefficient. There's that 1/. Now, we don't have to deal necessarily with all of these. The problem may simply be asking us to compare two of the rates. All right? And then one last thing, you notice that it's negative for our reactants and an implied positive for our products. So at this point, I can relate any two of these substances. Much like if I'm doing a stoichiometry, I can go reactant to reactant, I can go product to product, I can go product to reactant, I can go reactant to product. You can relate any two of these using this overall generalized mathematics. So let's try a couple more very quickly. We want to set that up for this particular reaction. So it says give the relative rates for the disappearance of reactants and formation of products. So let's take a look at this. This is our reactant, so I need a negative 1/4. And I'm going to use our simplified way of doing this, if my Mimeo will cooperate. The rate with respect to pH 3. That's phosphine gas. That's actually a pretty toxic gas. My husband's company works with that. And that's going to be positive 1/1. Now, it's been a while, but we've seen this P4 before. Phosphorus exists as that little, tetrahedron type cluster. And that would be the rate with respect to P4. And that's going to equal 1/6 times the rate with respect to H2. And just to really reinforce this, stoichiometric coefficients, it's 1/, the corresponding stoichiometric coefficient. Now, the next question will give us a numerical example of that. So let's move on to that one. We are on, remember, don't forget that I put the page number of your notes at the bottom of the slide in hopes you could follow that. Now, this question says, I want the rate with respect to N2O5 that was measured. All right, and I want to talk about those units there. They look harder than they really are. And I want to predict what it would have been with respect to NO2. So that's the overall gist of this math. Now, I want to look at these units a little more clearly. That's moles. Well, a decimeter cubed is equivalent to a liter. For those of you who are in IB uses decimeter cubed much more. And I think the medical industry tends to use centimeter cubed more than milliliters and probably decimeter cubes more than liters. So I'm going to substitute moles and I'm going to put liters to the -1 and then minutes to the -1. Now, if you have something that's a minus power, that simply means it's in the denominator. So that would be moles per liter. And that would be per minute. You'll see why I wrote it this way in just a second, I think. Well, that's molarity per minute, change in concentration per time. So just wanted to make sure I clarified those units because they are a little bit more unique compared to what you have seen before. Now, using my stoichiometric coefficients, and I'm not even going to pay attention to oxygen. The problem didn't ask me anything about oxygen, so I'm not going to set that up. But I would say minus 1/2, 1 over my stoichiometric coefficient, minus because it's a reactant, is times the rate. I'm getting a little ahead of myself here. Brain goes faster than the hand. Times the rate of N2O5. I just thought of an advantage of the flipped curriculum for you. You don't have to stop and help me find my coffee in between our problems. But you still have to see my goof ups as my brain goes a little faster than my hand. All right, back to the problem. Now we're going to take 1 over this coefficient, 1 over 4 times the rate with respect to NO2, nitrogen dioxide. Now, the problem gives me this rate. That's what that symbol means. And so I would have minus 1/2. Now I'm going to substitute into my given, and at this point the algebra is about as straightforward as anything you're going to see in this class. And that's 1/4 times x, our unknown rate. So if I do a little cross multiplying, I find that my rate with respect to NO2, which we set equal to x, and that is equal to 0.00166 molarity per minute. I prefer not to have my units in a denominator if I can help it. So I would have written this much like you saw in the problem. I would have written it as molarity and then minutes to the -1, or minutes to the -1 times molarity. Either way would have been accepted. Okay, so that is it for this portion of it. That's how we compare and determine rates. Determining rates from the graph, you'll have to sketch it out. Comparing rates, you'll be given values and you will have to do the mathematics with this to compare rates using their stoichiometry. So hopefully I've set the expectations well for you. And